I want to start this series on thermodynamics by talking a little bit about the key players in this topic and the zeroth and first laws of thermodynamics. Thermodynamics is trying to answer some pretty big questions, such as what is the relationship between heat and work in a particular system? Or how much heat is being exchanged between the system and the surroundings during a particular reaction? Or what will be the equilibrium composition of a system? How much will be reactants or how much will be products? When we're using the word system, I'm talking about the reaction or a particular group of reactions that we're most interested in, and then the surroundings or everything else that will be impacted by that system, by that group of reactions, but is not directly involved in it. The bottom line is that the laws of thermodynamics give us the information we need to understand and predict reactions without having to spend lots of time in the laboratory working directly with that reaction. It saves time, it saves money, probably prevents some disasters and some going down rabbit trails that are not going to work, because this gives us a greater understanding about why things happen, and it'll help us figure out what the best way to proceed on any particular problem. So who are the key players? Who are the components involved in thermodynamics? Well, the first one I want to talk about is the internal energy of a system. It comes in two particular forms. Internal energy is kinetic and potential. The kinetic energy is found in translational, vibrational, and rotational forms depending upon what particular elements or molecules are part of the system that you're working with. All elements and molecules have translational energy because that's energy of movement. And so we have little particles that are moving in a particular direction. And as the temperature goes up, the kinetic energy goes up, and they move even faster. And I think you probably have a sense of this from your previous chemistry courses, this connection between temperature and kinetic energy and the speed of things moving. But then if anything's larger than just a single monatomic element, it also can have vibrational or rotational energy. Vibrational energy is seen when you've got a compound. We'll just make a two-element compound here, and it's just sort of wiggling back and forth. The bond size, is shrinking and expanding. It's just sort of bouncing around in itself instead of bouncing off something else, which happens with translational energy. And rotational energy is when an axis then becomes an axis of rotation for that particular compound. And so all of these energies of movement, of motion, are part of the kinetic energy in the internal energy of any particular system. But also molecules have potential energy that's been locked up in chemical bonds and is also tied into the intermolecular forces that bring molecules in attraction with attraction to another molecule. And so that the energy in chemical bonds and in intermolecular forces is waiting there to be released. It's not energy of motion yet, but it can be converted. The other major component in thermodynamics is heat, and of course the thermo part of the name refers to this. Heat is thermal energy when it is being transferred from the system to the surroundings. We get an idea about the thermal energy of any substance by measuring the heat, because the heat is what we can measure. As it moves, then we can grab a hold of it and make a measurement. Thermal energy, in turn, is based on internal kinetic energy, and as I just alluded to previously, it's proportional to temperature, so that temperature is defined as the average kinetic energy. When we're talking about heat in thermodynamics, we're often looking at some specific types of heat. So specific heat, I just kind of repeating myself, and latent heat are two particular ways of looking at heat. Specific heat, also called heat capacity in some older textbooks, refers to how quickly a substance absorbs or releases heat. So different substances have different specific heat. Water specific heat is very high, metal specific heat is very low. And latent heat refers to heat that is sort of hidden as a substance is changing from solid to liquid or liquid to gas. We don't see a temperature increase as that phase change is going on, but heat is still being transferred, it's still moving in, and that's our latent heat. And I'll talk about those two particular kinds of heat more in the video that includes the problems for this set. So we've got internal energy, we have heat, and the third part of thermodynamics, and it affects or is reflected in the dynamic part of the name, is work. And work, of course, is relating to force, motion, force used to transfer energy both on a macroscopic scale, if we see things pushing or pulling on a system, deforming the system, or being crafted in order to allow that to happen, as you see in machines, and also on the microscopic level as particles interact and bounce off each other. Force then is involved in transferring that energy. So when it comes to thermodynamics, we're thinking about internal energy, we're thinking about heat, we're thinking about work. We're also thinking about temperature as a way of measuring heat. And temperature is based on a state of thermal equilibrium. So it's looking at what happens when two substances, and I'll just use a very common example, if a coffee cup full of hot coffee and a spoon come in contact, what's going on? Well, of course, first the coffee is hot and the spoon is cold, but over time the spoon becomes hot. So why is that happening? Well, we've got our kinetic energy, particles full of kinetic energy in that hot coffee, and they are moving, translational energy, and bouncing off the spoon. As they bounce off the spoon, that force then transfers some energy into the spoon, and these particles in the spoon, which initially are not moving very fast at all, very short little arrows, start growing longer arrows. But then this particle out here that has just bounced has lost some of that. We'll shorten its arrow up a little bit here. So it is no longer moving quite as quickly. So that over time, the average number of particles with high energy decreases in the coffee, and the average number of high molecules increases in the spoon until they are equal. Thermal equilibrium only works, though, when two substances are in direct contact, connecting to each other across a boundary. However, if you think about the principle expressed by the Zeroth Law of Thermodynamics, this shows how we can use a thermometer to actually determine the temperature of the coffee when there is not a direct connection. Because the Zeroth rule, or law, tells us that if there are two substances that are both in thermal equilibrium with a third substance, then those two substances are in thermal equilibrium with each other. So here I've drawn a beaker full of some liquid and our thermometer, and if you think about it, there's a boundary here between the glass of the thermometer and the beaker of solution, and there's a boundary here between the fluid inside the thermometer and the glass of the thermometer, but the fluid inside the thermometer does not touch the fluid inside the beaker. How can we use the fluid in the thermometer to tell us anything about the fluid in the beaker? Well, this Zeroth Law of Thermodynamics tells us we can. Because if the fluid and the glass are in thermal equilibrium, and the glass and the fluid inside the thermometer are in thermal equilibrium, then the fluid outside and the fluid inside are in equilibrium as well. And what is reflected on the scale of the thermometer is then an accurate representation of the solution in the beaker. So the Zeroth Law of Thermodynamics, which, as I said, arose in time after the first law, so they had to give us an interesting word there, is explaining why we can trust thermometers to tell us what the temperature of anything is, and that that temperature will actually reflect the kinetic energy of that substance. So finally we get to the first law of thermodynamics, which is just a restatement of the law of the conservation of energy, that energy can be converted from one form to the other, but it cannot be created or destroyed. What this law adds, though, is it tells us how energy is converted. It's converted by the interaction of these components, heat, work, and internal energy. And so we've got some specifics now to put with this general idea that energy doesn't go away, it just changes form. In fact, it can be put down into a neat and tidy little math equation that says the change in internal energy, delta U, you also may see this as a delta E, E instead of U, sometimes it's used, but the change in internal energy is equal to the heat transferred, either into or out of the system, and the work done, either on or by the system, so that you've got some specifics now with this first law. And we'll be working with these details, internal energy or heat, or possibly work, as you work the problems that are usually associated with this part of thermodynamics when we're learning about these concepts, which is the focus of the next video.